Hey guys, welcome back to another AP Chemistry video. Today we're going to be going over 1.3 elemental compositions of pure substances. In this subunit, pretty much what the title is. We're going to see how pure substances have their fixed compositions with different elements. So, as always, to start off with the joke of the day is going to be, why do chemists always trust pure substances? Well, they never have mixed feelings. Alright, let's get into chemistry. Alright, so let's remember what a pure substance even is. A pure substance can be a molecule. It's all pure elements, but the common ground here is that they all have fixed compositions, meaning that the elements' presence and the ratio of those elements are going to be the same. The opposite of a pure substance, for example, is a mixture. So a mixture can be mixing water with salt or water with sugar. So speaking of salt, let's look at that example for a pure substance. It's going to be a pretty common and pretty important example, sodium chloride, table salt. You know, those delicious crystals that you have on your fries. And the formula for that is NaCl. Notice here that we have a 1-to-1 ratio of sodium and chloride. It's going to be a fixed ratio. So every single molecule of sodium chloride is always going to be NaCl. Let's look at another example. One of the most important substances in all of chemistry and even in the world is water. We have H2O, and here we have a 2-to-1 ratio, always, of hydrogen to oxygen. So simply put is we have 1 mole of oxygen, there's going to be 2 moles of hydrogens. Now, every single example of these pure substances are always going to have these fixed ratios, no matter what it's from. Now, in addition to having these constant ratios, the mass is always going to be constant. Recall from subunit 1.1, we mentioned how we have to multiply the ratios of the elements in a substance to find the molar mass. Now we just have to remember that each element's mass will remain the same to make up the whole molar mass. That's basically how we're going to find the percent composition of these elements in a pure substance. Now, I know, such simple words can sound confusing, but let's look at an example to put the words into a problem. So let's go back to sodium chloride, NaCl. We know that the molar mass is 58.44 grams. Now, we want to find how much sodium makes up sodium chloride, how much chlorine makes up sodium chloride. Together, they should make up 100% of sodium chloride. So in order to find this, we're going to divide the molar mass of an element by the total molar mass of the molecule. So the molar mass of sodium is 22.99 grams, and we're going to divide that by the total molar mass of sodium chloride. And that gives us 0.3934. Now, since we want the percent composition, we're going to multiply by 100. And that's going to give us 39.34%. So now we can say that sodium makes up around 39.34% of sodium chloride. And you do the same steps for chlorine. The molar mass of chlorine is 35.45 grams. And divide that by the total molar mass of sodium chloride. And that gives us 0.6066 times that by 100. And we get 60.66%. So chlorine makes up 60.66% of sodium chloride. And if you add them together, that totals 100%, which is accurate. So I just walked you through how to find the percent composition of sodium chloride. I'm going to give you another example, and I want you to do this on your own. So here we have sucrose, C12H22O11. I want you to find the percent composition of each element, so carbon, hydrogen, and oxygen. Pause the video and try to solve this on your own. Alright, so I got 42.10% for carbon, 6.49% for hydrogen, and 51.4% oxygen. Now I'm going to quickly walk through the steps for this one because I kind of threw you in the fire there, but if you got it, good job, and you can skip ahead. Alright, so first let's find the molar mass of sucrose by multiplying the AMUs by the ratios of each element. So we have 12 carbons, multiply that by the molar mass of carbon, that gives us 144.12. Do the same thing for hydrogen, 22 times 1.01. That gives us 22.01 grams. And last but not least, oxygen. We have 11 moles of oxygen. We multiply that by 16. That gives us 176 grams. So total, adding them up, is 342.3 grams. Now we're just going to divide each element's mass by the total molar mass. So for carbon, that would give us 0.421. Remember to times it by 100. So that would be 42.1%. And same apply for hydrogen and oxygen. All right, let's move on. So why do we have to look at these percent compositions? Well, let's ask the question, can different substances have the same mass? And the correct answer is yes. For example, even though a chemical formula may be different, if they have the same ratio of the same elements, they will have the same mass in accordance to percent composition. Now, I know in 1.1 I said that even though you have 1 mole of a substance, that does not mean that the mass will be the same. But I was comparing apples to bananas in that situation. Like, I was comparing carbon to a more complex molecule like glucose. In this case, these substances have the same elements and the same ratio of these elements. So, in accordance, they will have the same mass. For example, if we have C5H11 to C10H22, the common ratio here is 5 to 11. So since the ratio is the same, they will have the same percent composition and the same mass, even though that the ratio here is bigger than the one here. So here we're comparing empirical versus chemical formulas. Now, remember those two terms, empirical versus chemical. Chemical formulas are the more complex version of a formula. So, like I said, C10H22 would be the chemical formula of C5H11. C5H11 would be the empirical formula. An easy way that I like to remember this is that the chemical formula is the unsimplified fraction, and the empirical formula is the simplified fraction. All right. So a common example for these empirical versus chemical formulas is glucose. So you have C6H12O6, and the empirical formula for that would be CH2O. And that's because we have a 1-to-1 ratio here. Now, remember again that even though the ratios are different, the mass is going to be same for both empirical and the chemical formula, and the percent composition will remain the same. So let's look at an example using these empirical formulas and how to solve for them. A compound is found to have 6.94 grams of potassium, 4.48 grams of nitrogen, and 2.04 grams of oxygen. What is the empirical formula of this compound? Use the molar masses from the periodic table as conversion factors. Alright, so the first step in these empirical questions is always to convert to moles. My AP Chem teacher would always say, when in doubt, convert to moles, and she's so true about that. So let's see how many moles of potassium, nitrogen, and oxygen we have. So we're going to use that by finding the mass of potassium and divide it by the molar mass in accordance to conversion factors, and we get 0.178 moles of potassium. Now follow the same steps for nitrogen, and that gives us 0.32 moles of nitrogen, and the same for oxygen, which gives us 0.127 moles of oxygen. Now here's a new step. Since we want whole number ratios, and we have decimals here, we're going to divide by the smallest amount of moles to get the whole number ratio. And the reason why we're using the small is we're using the element with the smallest amount of moles. It makes sense because if you divide by, let's say, the greatest number of moles, you're going to use up the least amount of element that you have. So that's why we want to use the least amount of moles. It's kind of like the reference, like you're as strong as your weakest link. If you only have a certain amount of this mole, you're going to use it up. So we're going to divide by oxygen. Alright, and that gives us 1 mole of oxygen, and that gives us 2.5197 moles of nitrogen, and 1.02 moles of potassium. So we have decimals again, but that's okay. Now what we're going to do is multiply so let's multiply by 2. If we multiply potassium by 2, that gives us 2.804, which is close enough for us to round to 3. And if we multiply 2 by 2.5, we can just get simply 5. Now that we have whole number ratios, we can make the empirical formula using these mole ratios. So the empirical formula for this problem would be K3N5O. Alright, so now I'm going to give you a percent composition question, and I want you to solve it on your own. But this time I want you to convert into mass from percents. Here we have a compound is found to contain 40% calcium, 12% hydrogen, 19.9% phosphorus, and 28.1% oxygen by mass. Now here's a little hint. Treat the percentages as grams. So if you have 40% of calcium, just treat it as 40 grams of calcium, and so on. And typically, you know how we say that we want to make up 100% of the molecule? Think of it as 100 grams of the molecule. Alright, pause the video and try it on your own. Alright, so the empirical formula for this compound is CaH4P2O7, or calcium dihydrogen pyrophosphate. Now, I don't want to make this video extremely long, so I'm going to put the calculations and the steps in the descriptions if you have any questions. Alright, I know this video is already long, but remember, this is the big subunit in the whole unit, and we're almost there, so keep going. So on the AP exam, you're going to most likely have 3 types of problems based on empirical formulas. The first one is just straightforward mass and pure composition finding. The second one is just combustion analysis. And just to go over combustion analysis, remember it's just burning oxygen and analyzing the amounts of carbon and hydrogen. And the last one is hydrate analysis. So you're going to be heating a hydrated ionic solid and analyzing the mass change to determine the mole ratio of water to the solid left behind. Alright, so let's go over the first one, which is just straightforward mass composition. Here's a problem, and try to pause it and solve it, and do it as quickly as you can because on the actual exam, you're going to have about 1 minute and 30 seconds to do it. Alright, so a quick run through. First, we're going to convert to moles. For carbon, we have 1.349 moles. Hydrogen, we have 2.673 moles. In oxygen, we have 0.506 moles. And since we have the least amount of oxygen, we're going to divide every single answer by oxygen. That gives us 6 moles of carbon, 16 moles of hydrogen, and 1 mole of oxygen. So the correct answer will be D. Alright, so now let's do a combustion analysis one. I'm going to walk through this one since we haven't gone over one like this, but if you want to try it on your own, go for it, pause, and skip to the results. Alright, again, like always, we're going to convert to moles first. And we're only given the mass of carbon dioxide and water. So we're going to have to derive the moles of carbon, hydrogen, and oxygen from this information. So let's find carbon first. And since carbon dioxide is the only molecule with carbon, we're going to derive it from carbon dioxide. So we know that the molar mass of carbon dioxide is 44.01 grams. Now we're going to divide the amount of carbon dioxide given, which is 33 grams. So in this case, it's going to be 33 grams of carbon dioxide by the molar mass of carbon dioxide. So we know that we have 0.4998 moles of carbon dioxide. Now that we have the moles of carbon dioxide, we're going to find the amount of carbon in this carbon dioxide. Now here's a quick trick. Instead of having to divide to find the percent composition, we can use these ratios. Now a lot of these stoichiometric equations are going to have a lot to do with ratios. So if you want to quickly find the mole ratio of something, just look at the ratios of the elements. So here we have a 1-to-1 ratio. So for every single carbon molecule, we have 1 mole of carbon. So since it's a 1-to-1 ratio, that means that we're going to have the same exact moles of carbon in a mole of carbon. So we're going to have 0.7498 moles of carbon. Alright, so let's find hydrogen now. Same thing applies, but this time we're going to derive it from H2O. So you have 27 grams of water, and since the molar mass of water is 18.02, let's divide to find moles. And we get 1.4983 moles of H2O in this reaction. Now let's look at the ratio again. But this time, for every mole of water, we're going to have 2 moles of hydrogen. So the ratio is 2-to-1. So in this case, we're going to have to multiply the moles of H2O by 2 to match the ratios. So 1.4983 times 2 is 2.996, or 3. So we have 3 moles of water. So now that we know the moles of carbon and hydrogen, let's finally find oxygen. And it's a lot more simpler now that we have the moles of carbon and hydrogen. So let's first add up the total mass of carbon dioxide and hydrogen to see how much we're working with. So 33 grams of carbon dioxide and 27 grams of water gives us 60 grams total. Now we're going to turn these moles into grams to find out how much oxygen we have by subtracting the mass of carbon and hydrogen from the total. So if we have 0.7498 moles of carbon, that's going to be 9.01 grams of carbon. If we have 3 moles of hydrogen, that's 3.03 grams of hydrogen. Now we're going to subtract that value from 60, and it gives, so it's going to be 60 minus 12.04, and that gives us 47.96 grams, which is the mass of oxygen. So let's turn that into moles. If we have 47.96 grams of oxygen, we're going to divide that by the molar mass of oxygen, which is 16, which gives us 3 moles of oxygen. So now that we have the moles of every single element. We're going to divide by the smallest amount to get whole number ratios, since carbon is not a whole number. So the smallest amount is carbon. So we have 1 carbon, and 3 divided by 0.75 gives us 4. And since it's the same for oxygen, is 4. So now that we have the ratios, we can tell that the answer is D. Finally, I know this is a long video, but believe me, it's extremely helpful to know this information. We're going to go over hydrate analysis. Now for me, these are a little bit more tricky, but this tricky does not mean hard. It just means that we're going to have a little more couple whats or has, but that's okay. So let's go over this question. It's an FRQ, so get those pencils out if you want to truly practice it. And pause the video if you know how to do it, but if not, I'm going to walk through it. Alright, so let's go over it. A student is assigned the task of determining the moles of water in 1 mole of copper 2 sulfate and water. The student collects the data shown below. Alright, so here we have the hydrate of copper 2 sulfate. The first question is, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. Alright, well, if we see that the initial mass and the first mass, there's an obvious decrease of around 2 grams. But by the third trial, we can see that there isn't much more of a decrease. So that means that there's no water left in copper 2 sulfate. It means that it has been heated enough. So that means that it's just going to leave the sample and the hydrate is no longer a hydrate because there's no water. So simply put, the correct answer would be, the hydrate has been heated a sufficient numbers of times because the mass of the sample does not change much between the second and third sample heatings, indicating that all water has been removed. Alright, so now part B, there's 2 sub-questions. Calculate the total number of moles of water lost when the sample was heated, and determine the formula of the hydrate compound. Alright, so the first subpart is to find the total moles of water lost. So lost mass usually always means that we're going to have to find the difference, meaning subtraction. And typically it's going to be the initial minus the final mass. So here we have to subtract the initial mass, 26.425 grams, by the final mass, 24.733 grams. And that gives us 1.692 grams of water loss. And now we're just going to turn this into moles by dividing by the molar mass of water. And that gives us 0.0939 moles of water loss. So that would be the correct answer for part B1. Alright, next, determine the formula of the hydrate compound. So essentially what we're doing is we're finding the missing number of moles of water in the formula of copper 2 sulfate hydrate. So we need our mole ratios again. We already have the water lost, so now we just need to find copper 2 sulfate. So in order to find the mass, we're going to subtract the final mass to the empty container. We're using the final since it has no water left, and essentially it's just the pure copper 2 sulfate without the mass of water. So 24.733 grams minus the mass of the empty container, which is 32.150 grams. And that gives us 1.583 grams of copper 2 sulfate. And now we're just going to find the moles of copper 2 sulfate. And the molar mass of copper 2 sulfate is 159.61 grams. So we're going to divide and we get 0.01 moles of copper 2 sulfate. Now we need to find the whole number ratios by dividing the moles of water by the moles of copper 2 sulfate. So it's going to be 0.0939 by 0.01. And that gives us 9.467 or 9 moles. Now this is a pretty big round, and most likely on the AP exam they won't give you a big rounding gap like this. It will be pretty obvious, but I made these problems, so bear with me with the decimals here. So the correct answer for the formula of the hydrate would be copper 2 sulfate times 9 moles of water. Alright, so thank you much for sticking around. I know it's a lot of practice, but these problems are super important to get down and will help you in the long run. I'm going to leave you off with one more problem. You can do it. Explanation will be in the description below. I know you guys are probably getting tired of my voice. Keep on studying, and you got this. Here's the problem. Alright, happy calculating!